Today we're going to talk about collision theory. Collision theory states very simply that molecules must collide in order to react. And so you see a picture here of two colliding molecules. The things that influence the reaction and the rate of reaction are listed at the bottom. Number one is the kinetic energy of the molecules at the time of collision. So kinetic energy is measured by temperature. And so higher temperature means higher kinetic energy. So the kinetic energy that they possess must be greater than the activation energy for the reaction. The concentration of colliding molecules traditionally influences the rate of reaction because the more molecules we have in solution or in the sample, the more often they will collide with each other and the more often they will result in an effective collision. And the third thing that matters is the orientation of the molecules. They should be oriented correctly in order to react. If they are oriented incorrectly, then the collisions will be ineffective. We're going to talk about all three of these a little bit more now. So temperature is a measure of kinetic energy. You can see this is a graph of the fraction of collisions along y and the energy of each of those collisions along x. So you get a sort of a relatively typical curve that has a maximum number of collisions with a moderately low collision energy. And the blue is the lower temperature and the purple graph is the higher temperature. And so if we increase the temperature of the reaction, then the number, then that shifts the curve over. And so if you look at the shaded region to the right, then that little dashed line represents the activation energy. That's the minimum energy that's required for these reactants to result in products. And so you can see if you look at the shaded region for the blue graph, it's very small. But for the purple graph, it includes not only the blue region, but also all of the additional purple region above it. So you can see that we have increased the fraction of molecules that have sufficient energy to result in an effective collision and to get products. Now, our second thing that matters is the concentration of colliding molecules. So if we look at that, we see a picture of a reaction. It's the same reaction on the left and the right, but on the left we are burning steel wool in the presence of air, which of course has oxygen in it. But if we take a flask that has a large concentration of oxygen, we fill it with oxygen, and we insert a burning piece of steel wool, then you see that the reaction becomes very rapid and very vigorous. And that is an example of how when we increase the concentration of oxygen, we dramatically increase the rate of this reaction. Now this is a cartoon that's meant to show you the effect of concentration. So the upper left-hand picture, that's just our normal that's our normal reaction that we're going to compare everything else to. So in this reaction we have molecule A, which is blue, and you can see it kind of flying through, colliding with the red B molecules in the box in the upper left-hand corner. And then box B, what we've done is we've doubled the concentration of A. So we have two blue spheres now, and you can see that the number of collisions has doubled. Now if we look at box C, what we've done is we've doubled the concentration of the red spheres, but we've kept the blue sphere at just 1. So we're comparing that to box A. So by doubling the red spheres, we also double the number of collisions. So that should also double the rate. So B and C should both be double the rate of A. And then D, what we've done is we've doubled both of them. So we've doubled the red spheres and doubled the blue spheres, and that has a more significant effect. That's going to quadruple the frequency of collisions and should quadruple the rate. Now our third little issue here is the orientation of molecules. So this is just meant to show you that if we have this reaction, and this is what we want to have happen, where A collides with BC, and that B atom leaves C and joins A, and that would be an effective reaction. But you can see that's the one in the middle there, but you can see if we flip BC around so that C collides, the C end collides with A, then that does not result in the effective collision that we were anticipating. And so the orientation of a molecule is very important.